Good morning, ladies and gentlemen. Welcome to our webinar, Utilization of HPC in Slovak Hydrometeorological Institute. My name is Lucia Maličková, and I will be your moderator today. I am happy to welcome you on behalf of the National Competence Center of HPC in Slovakia. Today's presentation will be given by Dr. Mária Derková from the Slovak Hydrometeorological Institute. She will speak about how she used high-performance computing for weather forecasting, climate modeling, and data analysis. Please, if you have any question during the presentation, please feel free to write them in the chat. Dr. Derková will answer them at the end of the webinar. Thank you for joining us, and let's begin. Dr. Derková, please.
Okay, so good morning again. My name is Mária Derková. I work at Slovak Hydrometeorological Institute. I was asked to give this talk in English, so I will apologize for my broken English. I will try to do my best. What I wanted to say from the beginning, I was asked to give this talk, maybe I switch off my camera, some time ago, but you may probably notice that the situation at the Slovak Hydrometeorological Institute is not very stable now, because we have got the fifth director general within the last 13 months. We are facing budget cuts, staff reduction, and so situation is not easy and not stable, let's say. But then I thought about it, and I decided that it would be a pity not to use this opportunity to present the outstanding work my colleagues are doing on our supercomputer. I hope So I put here just many colleagues on the title slides. I will try to name them as I will present their work. I really hope not to forget anybody. Do you see the next slide? Okay, yes. So this is the outline of my talk. I will explain why do we need a supercomputer at Slovak Met Service, shortly about its history and the current status of HPC. I will describe the main computer system or IT system which is running. This is a model ALADIN, and its various operational and research and development applications. I will speak about the ensemble forecasting and also other applications that are running. And if time permits, I will show you some, let's say, technical environment of our work on HPC. This talk is kind of a follow-up to the talk given my former colleague Josef Vivoda here within this framework of lecture series in March 2022. I hope the link which is here is correct, although you cannot click. So why do we need a supercomputer at the Slovak Hydrometeorological Institute? One of the principal roles or activities of our institute is to provide an information about the current state of the atmosphere, about its quality, about climate, water resources, and so on. And our next step is to provide information or produce a forecast and also warnings about the dangerous hydrometeorological phenomena. And this information is provided for the government, for the administration bodies, for crisis management authorities, and also for general public and many customers. Sorry, I'm doing something wrong because I have two monitors and I'm keeping within those. This information has to be accurate, has to be detailed, and has to be provided on time. And this is why we do most of these activities using the high-performance computer system. By the way, our HPC, which is the abbreviation I will be using all over the presentation, belongs to the Slovak critical infrastructure. So what we do on our HPC, we are doing the operational applications and also research and development work. This is about the history. Can you see my mouse now, if I'm pointing? We started, well, basically we started the work with the model ALADIN on the workstation version somewhere about in 1998. The supercomputer era began in 2004, when we acquired the first IBM supercomputer with only one node and 32 cores. And in the next years, we upgraded it twice, also with the IBM hardware. Each new supercomputer was more powerful, and we could do more on that. And so currently, our operational system is NEC. This is the Intel technology with 240 nodes, and this is what you see on the last picture. Here is the more like fancy picture of NEC with some technical details. As I say, we have 240 computational nodes on each node, so there are 40 cores, so altogether almost 10,000 CPUs, and which is a performance which can reach almost 650 teraflops per second. Here are some technical parameters. As I already mentioned, the number of cores. This is Intel. Intel CPUs joined with the OmniPath adapters. We have the Lustre file systems with RAID disk, and the total disk space is more than 1 petabytes. We are using Slurm queuing system. It's a Linux operational system. For the programs, we have Intel and GNU compilers. So this cooling and power supplies. And this is installed in the premises of Slovak Hydrometeorological Institute in Bratislava, here on Koliba Hill. So as I already mentioned, the main system, what is installed is the ALADIN model system. It's a numerical weather prediction model, which is designed for limited area forecasting with a focus on regional weather forecast with high temporal and spatial resolutions. The ALADIN system is developed within wide European and North Africa collaboration of 26 numerical weather prediction institute, national meteorological institutes that are grouped, that forms the so-called Accord consortium. The ALADIN is developed, so the consortium is named Accord, but the model or the system we are running is still called ALADIN for some legacy historical reasons. So the model is jointly developed. We share the source code and other tools which are necessary to operate the model. We have a common coordinated research and development within the Accord consortium, but the operational exploitation is fully in the responsibilities of the national meteorological institutes, or sometimes they form some smaller group to have operational applications. So I said we share the source code. So for the IT people, just this is a mixture of the Fortran and C and maybe some other tools. It's more than 2 million source code lines, and altogether development is estimated that it took 300 person years. I said that for the Accord consortium, we are 26 national meteorological institutes. Here it is on like nice graphics. Formerly, it was the basis is the ALADIN consortium, which transforms to new one, which is named Accord. We have also regional cooperation within Central Europe, which is named LACE. This is with these turquoise colors on the figure. And we also cooperate with the European Center for Medium Range Weather Forecast, which is like Google in numerical weather prediction. So the ALADIN model is the primary tool for short-range weather forecasting in Slovakia. It was already on the very first slide that we provide regular forecast warnings for the extreme weather. The ALADIN data are input for other downstream applications and the impact models like air quality, hydrology, road forecasting, and so on. We prepare data for public and private sector customers. Let's name the Aeronautical Service, Civil Protection Authorities, Nuclear Safety Authority, Public Health Authority, Transport, Agriculture, Energy, and also for the private sector, and also for the general public, mostly through our webpage. So the ALADIN system is, so it's one source code, but you can use it for various configurations. So this is a rather busy slide, but where is my mouse again? So we run on our HPC the limited area model with the different, let's say, mostly how you can distinguish is the horizontal grid spacing of your model. So the main one is what we call ALADIN SHMU, let's say. From what you know, most products on our webpage, it has a horizontal step about 4.5 kilometers. It's running 4 times per day, up to 3 days. Then we have two what we call convection permitting configurations. One is at 2 kilometer grid spacing, and second one is at 1 kilometer, and I will mention them in more details later on in my talk. And the Slovak Met Service is responsible for the operation application of the common LACE system, which is called ALIF, but this one is running not on our HPC, but at the CMWF supercomputer. So here it is, what was on the previous slide in table, here it is in graphics. So the main operational application, this ALADIN SHMU, is in the blue rectangle. This is the computational domain. The two small convection permitting configurations are running over this cyan or turquoise, or what is the color, smaller computational domain, and the ensemble system ALIF is covering whole Europe and its neighborhood. This is what it's displayed in red. Well, this is the sketch of many like infrastructure one needs to provide all the products which I showed. So in the heart of it is the high performance computer where the model is run, and also pre and post processing tools and where the products are produced. But also what we need is to collect the input data from the outside world, the observations, the data from global models. Once we run, then we have to disseminate the products to customers and also to our local teams which are using ALADIN data. And so that is what to show that the infrastructure for this is rather complex. And so to have it running, we need like many tasks to be done. All those tasks are performed within our NWP team at Slovak Met Service. The team is about 10 people, let's say. So, and what we have to do for operations, we have to do code porting, have to compile and build the executables. We have to run the model, those configurations. We have to master the download of the data, as I said, post-processing, visualization, verification, validation, product development, and monitoring, run and monitoring of all of this. Here I just highlighted that what we do as a monitoring is 24 hours per week, so it's non-stop. And most of the task has to be repeated also for the research and development. So how do we accomplish that? We are using a combination of tools. Those, as I said, are partly developed, maintained, and shared within the Accord community, and partly developed locally. What are we most proud of, and what I will describe in more details is a set of scripts which we call run app, like run applications. I will use the Slovak abbreviation run app because it's handy for me. This is used to run and monitor operational and research jobs. And we also have local tools for visualization, verification, and also the commercial software, which is used by the forecasting office and the aviation department. So this is like a graphical illustration of the tools we are using. So on the left, you see an example of the visualization of ALADIN products, which you might note from our web page. Then in the middle panel, you see kind of verification illustrations, and on the right panel, what tools we can use to monitor the observations which enter the ALADIN model data assimilation. So as I said already, I'd like to talk, or I can introduce you to our system, just run app. As I said, it's locally developed, and we have full control over it. It has a unified system for running and logging and monitoring of the applications. It is modular, portable, easy to modify because it's all developed by ourselves. It allows automatization of the model runs. And even if something goes wrong, we have the automatized way of sending the alerts to the responsible persons. Yeah, so here I especially like to highlight that this is the slide stolen from my colleague Martin Belush, who is the main developer of the system. So this is the visual example of how the system is used. For example, so if I go from the right side of my screen, you can see how we monitor the status of the HPC. You see, this is a screenshot from yesterday. So you see all the 240 computational nodes. In the green, you see the percentage of the utilization of the node in the actual one, real time. And here in red, you see that node 201 is currently out of the system. There's some problems. Then on the middle panel, you see the jobs which are running on HPC with different users, start and time, running time, status, and the nodes on which they are running. Here you on the left side, there is a monitoring of all jobs which are under the operational suite, let's say. You see that there are jobs which are running every 6 hours, but then we have jobs that are running hourly, and we have even higher granularity. We have a logbook, we call diary, where you can write down about you write down any information you would like to share with the colleagues about what's going on in the operations and new staff problems and so on. You can go even to the higher details. So it's interactive. So you click, and then you see the log of the application. maybe I've forgotten to say. So if it is green, it's completed. With D, you see that the application had some delay. If it's blue, it's running. If it's red, then it's failed. Yeah, you can see the statistics, which days, what was the finalization time of the run and so on. So it's very useful. It helps us a lot to monitor all the tasks we have to accomplish to fulfill all the data, to prepare all the data which I explained earlier. So we have a quite let's say, strong computer power. And so if you want to improve the forecast, it's tempting, or one of the ways how to do it is to just increase the resolution of your model. This is and to see how it performs. So here I also showed mostly the results of my colleague Andre Simon. So the motivation, as I said, is if you want to resolve small scales, with which often the high impact weather are associated, like supercells or flash floods or strong winds and so on. Then you may, one of the easiest things how to do is to increase the model spacing, like grid. Then you see more details, and you assume that the model can then resolve more topography related phenomena. So here you see the zoom of the model topography over Tatras, so high Tatras and low Tatras, and how it looks like if the model spacing is about 4 or 5 kilometers. And if you go down to hectometric scale, like 750 meters. So then you hope that, for example, here you would see the leeward downslope wind correctly resolved, and some thunderstorms which are developed locally and so on. Well, but the increase of the resolution is not sufficient, and you have to do other steps to adjust your model. So here it is an example of the case study of a thunderstorm which occurred on August 28 in 2023 that was associated with a strong wind gust. That is the color scale here on those pictures. So the more violet or red and violet, then the stronger the wind gust. So if I go from left to the right, so this is the forecast which was computed with the horizontal grid of 4.5 kilometers. This is how it looks in 1 kilometer resolution, 250 meters. And here you have the real observations. Of course, this is with only very few station measurements. What I want to say, if you go to with this picture, so if you go to higher resolutions, you might think that you see more details in the forecast. You hope it might be better, but actually, for this case, so the special so the patterns were not correct because, for example, here in this region, we missed the wind gust, which we have seen here. In more coarse resolution. Sorry. So this is another example. This was experiment run by Martin Belush. This is a simulation at 750 meters of the storm Boris. So this is with the floods occurred in September 2024 last year that hit, well, mostly Moravia, part of Western Slovakia, and windward side of the Alps in Austria. And it's simply amazing how details you. So I've forgotten to say that this is like 54 hours cumulated precipitation. So like total precipitation within 2 and something day. And it's amazing how detailed features one can see on this simulation with so high resolution. For example, here in Alps, you see that there were I don't want to say low, but the precipitation in the leeward side of the Alps in the valleys were not as high as the windward side. And so this is the illustration of the high resolution simulations. Why we need these high resolution simulations for the nowcasting, which is a forecast for the very short time, like several hours. This is the research, and so I named my colleagues in alphabetical order here. For these nowcasting purposes, we ran the ALADIN configuration with 1 kilometer horizontal grid, and this is run every hour, up to, let's say, 12, or for some ranges, longer forecast range. And why this is interesting is that so if you run every hour, you can have in your initial state more observations, more frequent observations. These are incorporated using the variational data assimilation technique. And so then you hope that with more observations, you can get better forecast because the initial state of the forecast is better, let's say. So this I will illustrate on the case of the Pohoda Music Festival in July last year, when the Slovakia, or Western Slovakia, was hit by the series of thunderstorms, and on the spot of the festival there was a big, large stage tent that collapsed, and there were several people injured. So here you see the radar picture with the reflectivities and the position of the thunderstorms. This is at 8 o'clock in the evening on 12th of July. So here it is how this was forecasted by our, if you remember the table with 3 columns. So this was the ALADIN operational application at 4 kilometers. There was an indication, and the array which I'm showing, the parameter is the simulated radar reflectivity. So what the model thinks radar measurement should see for the particular time and date. So here you see that there was some indication that there will be a line of thunderstorm developed. Unfortunately, this was completely missed with the 2 kilometer configuration. I will not talk further about, but for this rack system, it was again quite well forecasted. Now I will show the series of the forecast. So here you see the different, so the forecast valid for the same time, the forecast of the simulated reflectivity. So all the forecasts which you see are valid at so 18 UTC or 8 o'clock of the summertime, but they are starting from the different starting time. So 9 o'clock, 10 o'clock, 11 o'clock, and then you see. So what I wanted to say, so more to fresh the forecast, usually, or one would expect that it is more corresponding to reality. So here it is, so the situation for the 18 UTC, and then the same forecast, but 1 hour later for 19 UTC. Oh, sorry. So no, like this. So I go forth and back to show that. So that was quite nicely simulated with many details with what we call RAC, rapid update cycle application. Well, and some practical exploitation, because if you imagine that you are a forecaster on duty, and then you have to check the forecast every hour, then it's like too many data to check. So one can imagine like more smart visualization of those rapid update forecast that you can put them in, let's say, what they call post-time visualization. This is the slide I have taken from the diploma thesis of student Martin Petrovic. Well, I'm sorry for the resolution; it's not the best one. But what I want to say that you can put the subsequent forecast in a grid, let's say, and you see if the forecast match the radar reflectivities, then you decide if you can trust the forecast. If it is if the fresher forecast is more similar to reality or not. Well, now I would like to talk about ensemble forecasting. This is the way how we address the uncertainty in the forecast, because of course the atmosphere is a chaotic system, and we know from the mathematical theory of Edward Lorenz that like if it's transport to numerical the prediction, then it says that the phenomena or the matter forecast, for example, if you go to longer ranges, the uncertainty of the forecast is higher, and if you longer time ranges, I mean, and if you go to smaller scales, if you want to focus on the small scale phenomena, also the uncertainty in the time and localization is very high, and it is increased with the resolution. And how we in the numerical weather prediction address this is with the way of ensemble forecasting. So here at Slovak Met Service, this work is almost entirely done by my colleague Martin Beluš. So now I will show most of the slides I will show are coming from his work, so I will not acknowledge him on each slide particularly. So for the ensemble forecasting, as I said, we are Slovak Met Service, or Martin is responsible for development and operational application of the system, which is called ALAIF. It stands for ALADIN or ALARO Limited Area Ensemble Forecasting, running on this big red wide European domain at ECMWF supercomputer. And what I miss on this slide is that how the ensemble, what I mean by the ensemble, that we are running several so it's the same model with the but several what they call members here for this LA 16 members that are trying to simulate the uncertainty in the model. So we can simulate the uncertainty in initial conditions, and this is done by perturbing the observations and the first guess that entered to start the forecast. We can simulate the uncertainty in boundary conditions by using boundary conditions from different global model ensembles and do kind of what they call blending, a combination of those. Yes, so this is here that we have 16 members from the boundary conditions, and we simulate by blending the uncertainty in the initial conditions of those. Then we simulate the model uncertainty as such, using the different model physics setup with clusters for different model physical parametrizations. And we also do a perturbation by stochastic physics perturbation by surface prognostic fields. Yes. Right. So then, how does it look? Then we have 16 members, which comprise our ALIF ensemble, and this is the precipitation for this weekend, actually, for last weekend. And you see that each ensemble member gives slightly different forecast. The point is that all those forecasts are equally equal in their like say probability. I mean they are equal. Yeah, they are equal. And then if you want to give some concise information, then you can from this ensemble produce like ensemble mean ensemble minimum, ensemble maximum, and ensemble spread. And then you see how probable is the forecast of particular parameter. This is how we visualize in the maps. Okay, so this is another visualization. So again, I come back to Storm Boris, September last year with the floods which occurred, and here you see actually the forecast which was run for 4 days ahead, and you see the total precipitation accumulation for this period. And actually the minimum and maximum of the ensemble and the spread, as I said. And you see that the maximum very well corresponds to the places where really the floods occurred. So how to show this information, or how to explain this information to, let's say, to the public? You can do a point visualization, what we call EPS grams, and then you can show that you can plot, let's say, all 16 members of the ensemble, the time evolution of a particular parameter. Here you see the temperature in cold of, let's say, we call it spaghetti visualization. Then you can do an envelope of all scenarios showing the ensemble mean, which is on this middle graph with the red dashed line, and then you see the maximum and minimum. And then you can show percentiles or quartiles, and that's maybe not, so maybe here it's better visible that you have 25 and 75 percentile with an envelope around the ensemble mean, and then you have maximum and minimum. And then you can see what is the spread of the various forecast scenarios, and then you can judge how probable is the evolution of the forecast itself. This is what you can see, what you can find on our web page. The two pictures on the left are static products, and the last one on the right is interactive one which uses the high charts technology. So it means that you can zoom it and see, let's see more details if somebody is interested in. What can you learn from such an example? This is the example of temperature forecast, and you see that those different scenarios actually form two clusters here on this two spaghetti distributions, let's say, and the ensemble mean, which should be like the most probable forecast, is in the middle, and actually it's just for this it's purely statistical. If you see how it verifies, this is on the bottom graph, where in the red color there are the observations, I mean the real measurements. And what is very interesting here, you see that for the daytime, the reality follows the let's say warmer scenario, warmer cluster, and then during the night it actually follows the colder scenario. And maybe what is interesting here in the green color is the operational, this ALADIN application, which is running here locally, and you see that this is within the ensemble spread. But actually the forecast for the night was not correct of the, let's say, more operational application. Here is also a rather similar example, that there were two different clusters of the forecast. Here the operational ALADIN followed the upper one, but actually what was realized was what really happened was the colder cluster, colder forecast, which corresponds also to ensemble mean in the blue color. So, and how to like conclude with this? Why we need ensembles? We can show by this illustration that the ensemble mean of this LIF, if you compared it with the deterministic ALADIN SHMÚ model, the ensemble mean in the longer range is always better than any deterministic forecast. So here you see the bootstrap visualization or verification using triangles. If the triangle is blue, then it means that the LIF mean performs better than the operational ALADIN. So you see the various verification scores, root mean square, mean absolute error, standard deviation, and bias. And here you have the parameters like 2-meter temperature, relative humidity, mean sea level pressure, and wind speed. So the message you have to take is that the ensemble mean outperforms any deterministic model for the long verification period. So this was using, this verification is done using the HARP tool, and I thank to Martin Petraš for this picture. So what you can do also with the ensembles is that you can have many very useful products for the warnings for the extreme weather. Here I show something which will be a new with a new development. Then you can forecast or identify various precipitation types. One of those is freezing rain. Here on the maps displayed in red color. So again, on the left, you have for particular date, 16 members. This is the precipitation forecast, total precipitation. And on the right panel, you see the different precipitation types. And then if you check the particular one, here, this red one, which is the freezing rain, this is for the case where it really happened, then you can compute the probability of freezing rain product, which and this is the case which illustrated and where it really happened in January. No, it's January last year in Bratislava region. Is it last year? Yes, it's last year. Another interesting product you can compute from the ensemble is the precipitation state. This is not new. This is existing product that you can distinguish how big part of precipitation will be in form of the, I mean, in probabilistic manner, how big part of precipitation will be in the solid form and in the liquid form. So snow in the green, rain and in blue. And again, this is a typical composition. So ensemble mean, ensemble spread, on the bottom ensemble minimum and ensemble maximum. So here it's verification against the real case, where on the western southwest Slovakia, it was really raining, and on the rest of the territory, it was snowy. Another visualization of this, this is a different case, but you can compute the precipitation of the probability of precipitation for different threshold. You can see the ensemble mean of this total precipitation. And again, you can check whether it was in the solid and liquid state. So the light precipitation in the western Slovakia were mostly snow, and the more heavy precipitation in east and south were in the liquid form. And again, this is all probabilistic product. Okay, now I'm running maybe out of time, but now I will show you the impact applications or downstream applications which are running on our HPC and are getting the data, input data from the ALADIN model. The first one will be flood prediction. So here are names of my colleague from the hydrological department and also two colleagues from the NWP department who are cooperating with them. So for the hydrological modeling, one has hydrological models which predict the discharge and the water level on the particular locations, and those take as input the precipitation and temperature fields from the atmospheric model for ALADIN. And also they take the real state, the atmospheric, the, let's say, analysis of the precipitation. I mean, analysis, let's say. And this can be provided to hydrological models as either gridded data or mean values over predefined river catchments. So here is the map of the catchments which are actually used for our hydrological models. And we have two of these models. One is HBV. This is installed on Windows workstation, so I will not talk much about that. And there we have a, HEC model, which runs on HPC. So this is the work of my colleagues. And this is a scheme showing that we have the pre-processing tools that format model inputs to a specific format which is needed for the HEC model. Then you have configuration files and the model itself, and which runs the forecast. And this is done on HPC. Also, the hydrological models are attempted to increase their resolution to get a better or more detailed forecast. So here is an example of the Hron River Basin with the endpoint of Banská Bystrica, and this was with the lower resolution. There were few sub-basins, and then you have much more for HBV model, and the same for the HEC model, which can get gridded data, not the average of for the sub-basin, but the original gridded data. So how such a forecast is performing? Here I'm showing the flood situation in May 2021, I think, in Banská Bystrica. So for these river catchments, which I showed on the previous slide, on the very first panel, you'll see the real precipitation, which were observed. Then on the top line, you have the forecast of the HBV model. On the bottom of the HEC model. With the black dots is the real river. This actually this is the I mean the water level or discharge. I'm not sure. What I want to say is that in reality that there was the third level of the floods warning which really occurred. And so with the colors, you have a different model runs. And the meteor forcing, which was provided for that 4 kilometers, 2 kilometers, and 750 meters. And generally, one would expect that with higher resolution, the model forecast would be better. I mean, closer to observed values. Yeah, and this is the example from the publications, which is referenced here on the right. Then the ALADIN data are used for the air quality modeling. Again, here the list of my colleagues who are working on that. So the air quality modeling, they are taking data from our 2 kilometer resolution model, which is running twice per day, up to 3 days over this turquoise rectangle domain. What they do, they are using the CMAC model. This is the air quality model where the inputs are the meteorological data, 2D and 3D meteorological arrays from this 2 kilometer ALADIN configuration. They are getting the boundary data from the aerosols measurements, let's say, and from the national emission inventory of emissions. Then they have a meteorological preprocessor on the ALADIN data. Then they run the model, and they compute the concentrations of particulate pollutants like PM10, PM2.5, ozone. This is, I don't know in English, nitrox dioxide or something like that. So here is how it looks. Those are the hourly concentrations of this nitrox pollutant. Here you can from the road transport. So here you can see the main highways in Slovakia. This is the PM10 concentration of PM10 particles from the local heating. I'm sorry, I don't know the date. This was just an example we have on our web page. And this is the ozone concentration, I think, from yesterday. So these are data available daily. It's computed twice a day, and it's hourly forecasts. And then they also do like yearly quality assessment of the air pollution of Slovak Republic using the same input data. And so this is the yearly mean annual concentration of sulfur, again, I don't know, dioxide probably in 2025. And also you can find this on the web page. So the remote sensing department, they are also doing processing of the big data from the satellites and radar measurements. The application I would like to highlight is that it's the precipitation analysis, which is the information how much precipitation occurred over the territory of Slovakia, and it's computed from the radar and rain gauge data. Well, it's named the QPREDS. It's computed every 5 minutes as input. It uses 6 radar data and radar sites and about 300 automatic rain gauge stations. Here I show again from the storm Boris precipitations which are measured with the previous version of the original version of the software, which is called Rainbow, I don't know. And here in the colors, you see the estimated precipitation amount within 1 week or accumulation. You have to notice that the highest colors are in gray. And when in dots are the automatic measurement stations. And what you see is that there are many let's say wrong estimations by radar compared to the real measurements by the stations. So with this new QPREDS product, you got much better match of the real measurements with the radar estimates, and this can also be seen as a evolution of consequent improvement of the forecast, because you can get your original estimate or product, and then you can add more automatic weather stations that, for example, here they corrected the wrong estimation in the eastern Slovakia. Then you add to your input data the hydrological stations. Again, you have improvement here in this region of the Lee wave side of the small Carpathians. And you can also add amateur stations. Yeah, you have to control them, but also they improve the real situation measurements or real situation estimate by using more data. Climatological, how the HPC is used by the climatological service. The example here is illustration for the drought research and monitoring. Here I will be showing the a specific parameter, which is called standardized precipitation and evaporation index, that accounts or uses the input for the precipitation and the potential evaporation, evapotranspiration, to assess the drought conditions. Yeah, so, and if one remembers from the previous slide how uncertain can be the precipitation forecast, then to take this into account correctly, one has also to use the ensemble approach. So this is the example of the ALIF 3-day, so the 16 members, you remember, no, this is precipitation, a 3-day forecast of daily precipitation total for the 3rd day and the mean temperature. And you see the high variability of that forecast. If you go to global model forecast, this is DCMWF, it has 50 members ensemble. So then this is the 7-day forecast again on the precipitation and temperature, and you see that the variability is even higher. So, and to take this into account correctly, one can compute this SPI index in the so you can compute the mean value of that from the ensemble, or you can compute the percentiles. So here I show 10 percentiles and 90 percentiles, and with the colors you see the drought if it is red, and the wet value of the index if it is blue. And this is the 3-day forecast and 7-day forecast example. Yeah, so if I still can show you some slides. I advertise in my abstract that I might be talking about machine learning, but I will not. I can just say that we are watching what our other European colleagues are doing in the machine learning and artificial intelligence in NWP, and it's really exciting, but unfortunately we do not have manpower for that. Another technical ongoing work is the code adaptation of the ALADIN model to GPUs, because now we are running on CPUs only, or the code is our code is available or working only CPU. So there is an ongoing work for adaptation on GPUs architecture, which allows us or will allow us to run on different Euro HPC infrastructure like Lumi supercomputer in Finland. What I will mention is that we are in the process of code transformation from what we call double precision representation of the values of numerical values to a single precision, which means that in single precision you will use the representation of floating point numbers on 32 bits instead of traditional 46, which has a practical impact, which can reduce the runtime down up, so we can reduce by 30 to 50% without losing the quality of the forecast. So this is ongoing work. I will show you the experiments by my colleagues, which I name here. And this is the precipitation, maybe only the convective precipitation forecast for the same date. One is running with double precision and the second in single precision. And you see that the forecasts are different, but the main extreme, or not extreme, but the high maximas are somehow captured. And if you have still 5 minutes, I might show you how the practical work on our HPC organized. So for example, we have different or individual users for everybody who wants to work on HPC. This is based on our LDAP manager within the institute. But for the operational users, for the tasks that are running regularly and producing the forecast, we have specific operational users. And then we have for the shared tools, just another user where we shared visualization or verification on whatever tools we have in common. So how it works then, if somebody wants to develop new application or to test something, he is doing it under his individual users. And once his work is finished or mature enough, then it goes under the operational user where it is run regularly. To share the supercomputer, we are using a workload manager, which is called Slurm. And thanks to its, so we submit our jobs, computing jobs to the queues. For standard user, we have user or long to, if it is for short or long. Yeah, I mean the task. But if something goes under the operational users, it gets a high quality queue, high priority queue, which is called high, and we can suspend our jobs, other jobs when there is not enough resources to run the high queue jobs. And also we can use we have the possibility to define job dependencies for several tasks, which I will show you. So this is the, you might remember, I have already showed this. You see the current, no, this is not current, this is a screenshot from the jobs which were running on our HPC. And so here you see the class or the queue. So here are the jobs, operational jobs which are running in high queue with the priority. And here is the user queue where the normal jobs or standard users are running. Well, this is not might be seen so well, but so this is the list of applications which have to run that can either run parallel because they are not dependent. So then you define, this is the configuration file for the set of series of applications which has to run. So some of them might have no dependency, but another applications may start only when the previous one, which provides the input data, is finished. And this is, yeah, so this we can do. Yeah, so and my last slide is, so as I said, I tried to name my colleagues which works I have presented, but I might forget some of those, and also some are doing more technical work which is not that visible. For example, on the web page, or if somebody is presenting some scientific outcomes. So here is the list of those who contributed, maybe not so obviously, but definitely very importantly for this is the NWP group. So I like to thank to all my colleagues with this. Yes, and this was my last slide. Sorry for taking all the time.
Thank you very much, Dr. Derková, for interesting presentation. It was really nice. And now it's time for your question. And we have in the chat first question from Pavel Gajdos. Please, Dr. Derková, can you answer? Is the forecast with better resolution available also for the public?
No, this is not yet available for the public. This is also only for our forecasters and deviation methodologies. Yeah, once it is mature enough for the operational usage, it will be for sure also available on our webpage, but not yet.
Thank you. We will wait for another question. And for example, I have one question. You spoke about the AI in the future. What do you think when you will start with the using AI in your forecasting?
Well, so in forecasting as such, you can already start because for example, the European Weather Center is running they call it, how do they call it? AIFS? Yeah, so the global model, which I used to refer sometimes. So our forecasters, if you ask about the forecast, they can already use the products which are freely available from the European Weather Center. But to do it locally, for example, in Slovakia, you will need, so we don't have staff, let's say, for that. It needs like big preparatory work, because although the tools for the AI are like open source and freely available, you need the input data on which you train your AI tools. And this you have to prepare. Usually it is done on several years or tens of years of reanalysis of your local model. And then so you need people who will do that. You need the CPU. You need well, special architecture. Usually it is done on GPUs, which we don't have, but we can use the Euro HPC infrastructure for that if we want. But yes, so what if I can judge from the other institutes, it's like several years of work which is needed. But what we already started is to use AI in smaller tasks, like quality control of the observations. This is a research work of it, cooperation with some students at the Communist University. And also we have applied for several projects with other universities or other companies. So it starts slowly, but I have no estimation when it will be used operationally.
Thank you very much. Okay, we will wait for another question. We have little time. Okay. I think we have another question. Okay. Now, thank you very much, Dr. Derková, and all for joining us today. We hope that the webinar was useful and inspiring for you. Have a great day, and we look forward to see you at one of our next events. Thank you again, and wish you a beautiful day.